In a Markovnikov addition, you would expect the rich to get richer. So you would expect a large group to add to this carbon and a small group to add to this carbon. In this video, we're going to look at two cases where this doesn't happen, where we have a backwards non-Markovnikov addition. The first case is where borane starts the reaction. In previous additions to alkenes, we've usually seen the electrons in the pi bond be attracted to a partially positively charged hydrogen. But that's not going to happen here, because this borane is very unique. Because the element boron is less electronegative than hydrogen. And as a result, the bond polarities point away from boron and toward the hydrogens. So this is a rare example where hydrogen has a partial negative charge, and the boron in the middle has a partial positive charge. So the negative electrons in the pi bond are going to be attracted to what's positive, which is the boron. And now a lot of things start to happen at once. A bit of a bond starts to form between the boron and the primary carbon, because remember that primary carbon doesn't want to be a carbocation. At the same time that happens, the other carbon, the secondary carbon, starts to take on a bit of a positive charge, because it starts to become a carbocation because of the double bond that's breaking. So all these things are happening at the same time, and there's another thing that starts to happen. As the carbon here gets more positively charged, it gets more attracted to the electrons here in this bond between the hydrogen and the boron, and a bond starts to form between the hydrogen and the secondary carbon. You have all these things happening at once. In the reactions we've seen previously, there's been a carbocation intermediate, and then something adds to the carbocation later. But this is a concerted reaction here, which means that everything happens at the same time. And the result of all these things happening, well, you can just look at the two arrows. The result of these two electron movement arrows is this. And that's not usually the end product, though, because some other stuff will happen. And the boron group is usually replaced by something like a hydroxyl group. And that's how a poor carbon can end up getting the larger group added to it. And that's a non-Markovnikov addition. Here's how the addition of a hydrogen halide can lead to a non-Markovnikov product. It's if you have peroxide. What the peroxide does is it forms a radical, and that totally changes the mechanism of the reaction. Let's use hydrogen peroxide as a simple example of a peroxide. Now it's going to do a bit of reacting before anything even happens to the alkene. Peroxides are notorious for liking to make radicals. So what happens is that one electron from the bond will go to one oxygen, and I draw a little fishhook arrow here to mean that one electron is going. And then the other electron from that bond goes to the other oxygen. Half of the arrow tip means that only one electron is moving. And the result of this is two radicals. Because remember, a radical is a species where there's only one electron in an orbital. And they're pretty highly reactive. So they will steal a hydrogen from the HBr. The radical electron here is going to be used in the bond, and one of the electrons in the HBr bond is going to be used. And the other one's going to go back to the Br. Here's the hydrogen that got stolen from the HBr. And here is what's left of the HBr. It's just a Br radical. And it is neutral because it does have the other electron pairs, but it is reactive because it's a radical. So it's going to come, finally the alkene gets to react here. That bromine radical will add to the alkene before the hydrogen adds to the alkene. And there's going to be more fishhook arrows. One electron moves from the bromine, and one electron moves from the pi bond, and the other electron from the pi bond goes to this carbon. And the result of that is that the bromine bonds to the primary carbon, and the secondary carbon is left as a radical. Why doesn't the bromine radical bond to the secondary carbon? Well, the stability trends for radicals are pretty much the same as the stability trends for carbocations. A secondary radical is more stable than a primary radical. And now the radical needs to react with something else because it doesn't want to be a radical. And it finds an HBr, and the bromine ends up with the radical. And so it's kind of like a game of hot potato with the radical. Nobody wants the radical. Everybody's moving it on to the next atom. And our story ends here with the formation of the non-Markovnikov product, where the poor carbon has acquired the bigger group.